All right, we're going to start with eigenvalues and eigenvectors. It is a well-known topic in linear algebra and even differential equations. Um, First, let me introduce, in case we do not know the letter lambda. The letter lambda is this. This is the symbol, and that is the lowercase Greek, and that is the way we pronounce it, lambda. We're going to be using that letter throughout this video. So I wanted to introduce it. If you have an n by n matrix, so we're going to assume that A is n by n matrix, so a square matrix, and X is a column vector. Assume that X is a column vector, so X is a n by 1 matrix. We want to find the vectors that when we multiply this, we end up almost with the same thing. Notice that I left a blank here. We're not going to get exactly always the same vector. Sometimes we will, but we want to find the ones that are almost invariant under this multiplication, the x vectors that are almost invariant. They're going to be almost the same, except that we might have to multiply by a constant, which we're going to call lambda. So if we have a matrix, multiply with a vector, and we end up with almost the same vector, except that we have to multiply with a scalar, lambda, with a constant lambda, then that vector is a special vector, and it is called an eigenvector. That lambda corresponding to that eigenvector is called the eigenvalue. So the lambda is the eigenvalue, the x is the eigenvector, which is the same x as that one. So those are the same x. Okay. It is important to be able to figure out those eigenvalues and eigenvectors for any kind of a matrix. The method we typically use is that we find the lambda first, and then, or the different kinds of lambdas, and then we find, once we know the lambdas, then we find the eigenvectors. So the lambdas are the eigenvalues, and then the eigenvectors. Let's manipulate this equation a little bit. So if we multiply by the identity matrix of the same size, n by n, that does not change this right side of the equation, because again, multiplying by the identity is like multiplying by 1. It does not change the multiplication. Then we can subtract both sides of the equation, and then we have ax minus lambda I x equal to the 0 vector, the column vector 0. And that means that we can factor out the x, so a minus lambda I x is equal to 0. So we have a matrix. This is an n by n matrix. This is an n by n matrix multiplied with a scalar. It is also an n by n matrix. And so we have an n by n matrix. When we subtract, we have a square matrix multiplying with a column vector should be equal to 0. Now we either have one solution or we could have multiple solutions. If this is invertible, then we have a single solution, which is going to be the vector 0. But if this is not invertible, then we will have multiple solutions. And most of the time, we're going to have multiple solutions. So we are going to assume that this is not going to be 0. Rather, that this is not invertible, that we cannot invert it, which means that we have a singular matrix. Okay, so since we assume there are multiple solutions to this equation. See, if this was invertible, there would be a unique solution, only one. So then a minus lambda I cannot be invertible. since we assume there are multiple solutions, comma, a minus lambda I cannot be invariable. And if it is not invariable, then the determinant has to be 0. So determinant of a minus lambda I has to be 0. So this is the equation we come up with. This equation is called, well, after we develop the determinant, this turns out to be a polynomial on lambda, and that is called the characteristic polynomial of the matrix. So that leads, which leads to the characteristic polynomial of A, of matrix A. So the characteristic polynomial will be the determinant of A minus lambda I. That is the characteristic polynomial, and we're going to find the roots of that characteristic polynomial, which is going to give us, those roots are going to be the eigenvalues, and then we go through the process of finding the corresponding eigenvectors. Well, that's a lot of things going on. I think at this point we can start an example so that we know what is going on. So example 1, in all of these examples, we're going to find the eigenvalues and corresponding eigenvectors of the given matrix. So find the eigenvalues and the eigenvectors of the matrices we're going to write down. So let's start with the matrix A. 1, 2, 3, and 4 should be okay. Okay, so let's find the eigenvectors and eigenvalues. Okay, so first let's focus on the determinant of this matrix. So we have the determinant of, let's put this in a bracket, 1, 2, 3, 4, and then we're going to take away. Now lambda I means lambda 0, 0, lambda. It is an identity matrix, and instead of having ones in the main diagonal, we're going to have lambda and lambda in the main diagonal. Okay, so that is the determinant of the matrix 1 minus lambda, 2 minus 0, 3 minus 0, 4 minus lambda. And we know how to figure this out. Multiply those two, 1 minus lambda times 4 minus lambda minus 6. And then we have to FOIL this out. So we have 4 outer terms minus lambda minus 4 lambda plus lambda squared, and then we still have this 6. Let's put the lambda squared first. Minus 5 lambda minus 2. Oh, I was afraid this was going to happen. I just came up with a random matrix, and this polynomial is not factorable easily. Anyway, this polynomial is called the characteristic polynomial. Let me double check though. We got lambda squared minus 5 lambda plus 4, but then we got to subtract the 6. Well, it is what it is. So this is the characteristic polynomial. Of A. A is the original matrix. That is the characteristic polynomial. The roots or the zeros of this characteristic polynomial will be the eigenvalues of the matrix A. So we will have two eigenvalues. We have the same number of eigenvalues as the size of the matrix. So this is 2 by 2, so that means we will have two eigenvalues, including repetition. Sometimes we will have repeated eigenvalues. So let's move on to figuring out the eigenvalues. We have lambda squared minus 5 lambda minus 2. So lambda squared minus 5 lambda minus 2, and we want to set it equal to 0 so we can find the values of lambda. I know this is not going to be easily factorable, so that doesn't work. The factoring method doesn't work. We can use the quadratic formula on lambda. So A equals 1, B equals -5, C equals -2. And remember the formula, in this case, lambda is the opposite of B plus or minus the square root of B squared minus 4 times AC. All of that over 2A. So the opposite of 5, rather the opposite of -5 is 5 plus or minus, and then we're going to have 25 because that is the 5 squared, minus 4 times 1 and -2. So that is going to be -8, but we're going to subtract that. So we're really adding 8, 4, yep. And then all of that over 2 times 1, which is 2. Yeah. Unfortunately, we don't have very nice eigenvalues. So we have 5 plus or minus the square root of 33 over 2. All right, so we got two lambdas. We can label them as lambda 1, which could be 5 minus the square root of 33 over 2. I don't think it matters which one you label as lambda 1 and which one lambda 2 is, plus the square root of 33, all of that over 2. So there are two of them. And again, I label this as lambda 1, but that is totally arbitrary. If you label this as lambda 1, I don't see anything wrong, as long as the numbers are correct. But there's more to it. Now we have to find the vectors that correspond to those lambdas, the eigenvectors. Those are the eigenvalues. So lambda 1 and lambda 2 are the eigenvalues of matrix A. Next, we need to find the eigenvectors. Now, mind, that is a complicated number, but let's plow through it anyway. Okay, so we want to find, let's find finding x1, which is the vector, the column vector that will correspond to this eigenvalue. Now, what does that mean? We got to go back to the definition. The eigenvector is the vector so that when we multiply the matrix with the vector, we get back the same vector times the eigenvalue. Okay, so the matrix in question is the matrix A in example 1 is 1, 2, 3, 4. 1, 2, 3, 4. And we want to find a vector x1. I'm going to use A and B, so that we end up with A and B, again, A and B. So this is a little bit invariant. It keeps the A and B almost invariant, except that we're going to multiply with a scalar, and the scalar will be 5 minus root 33 over 2. Now let's go through this. So we have a system of equations, two unknowns, the same two unknowns, and one equation, one matrix equation. That shouldn't be too bad. Let's see, a plus 2b, a plus 2b should equal 5 minus root 33, 5 minus root 33 over 2a. So we're multiplying this times that. While 3a plus 4b, 3a plus 4b is equal to 5 minus root 33 over 2b. And we are solving this system of equations for a and b. Well, we want to really, and that's what makes this problem difficult, that we have really, really weird fractions here. Okay, so I'm going to move this to the left side of the equation, and I'm going to move this to the left side of the equation. So we're going to factor out the a. Yeah, so we have 1, the 1 corresponding to this, minus the fraction 5 minus square root of 33 over 2a plus 2b equal to 0, while here we have 3a plus, and then we have this 4, but then we're going to take away 5 minus root 33 over 2b, and that is going to be equal to 0. So those two equations have become those two equations. Let's simplify this. This is the same thing as 2 over 2. 2 over 2 minus 5 over 2, well, that is going to be negative 3 over 2. So this equation becomes negative 3. Well, let's keep the next part, plus square root of 33, all of that over 2a, okay, plus 2b equal to 0. On the other hand, here we have 3a plus, all right, now let's do this subtraction. 4 is the same thing as 8 over 2. If we multiply by 2 and divide by 2, we end up with 8 over 2. We're going to take away 5 over 2. So that's going to give us 3 over 2. But then we also have double negative here. So plus root 33 over 2b equal to 0. So now we have a nice system of equations. And we want to know the value of a and b that will work. I'm trying to think whether we want to substitute or eliminate. I mean, this makes, or maybe we can use Kramer's rule also, multiplying those two. But then we have to put the zeros. Wait a minute. If we put the zeros and the zeros there, if we put the zeros, maybe we can use the determinant. Yeah. I'm still thinking how to, those fractions are bothering me. Let's multiply by 2. So this equation by 2 completely, and we will have just negative 3 plus 33, negative 3 plus the square root of 33a, and we're multiplying the whole equation by 2, so plus 4b is equal to 0. And then if we multiply this equation by 2, we end up with 6a plus, and then 3 plus the square root of 33, quantity 3 plus the square root of 33 b is equal to 0. Yeah. And then we want to solve for A and B. I'm thinking what will work best. Let's use the Cramer's rule, as long as we have the Cramer's rule handy. So the determinant of the system is going to be the product of those two minus the product of those two. And the product of those two, when we multiply, is going to be 33 minus 9. Take the time to actually multiply those two binomials. It should be 33 minus 9 when we multiply those two binomials. But then we got to subtract a 24. So 33 minus 9, it's 24 minus 24, which is equal to 0. That is a problem. Let me check what's going on with this problem. Well, the problem is that 0 means we cannot use Cramer's rule. Boy, that was a shocker. All right, so Cramer's rule is out the window. Now, what we could do is use elimination to try to eliminate the a's. Boy, this problem was more than what I wanted to do, but that's okay. Let me label this equation as equation 1 and this as equation 2. We're going to multiply equation 1 by 6 to match the 6 here because we want to eliminate those two. Yeah. So we have 6 times negative 3 plus square root of 33a plus 24 b equal to 0, while we multiply the second equation and multiply equation 2 by negative 3 plus root 33 to match that. So this one already has a 6. We're going to multiply with that. We're going to end up with 6 times negative 3 plus the square root of 33. A, 6 multiplied with this A. Then this guy gets to be multiplied with the same number. And we did that multiplication here. That is going to be 33 minus 9, which is 24. Oh, plus 24b equal to 0. Okay, so that was very difficult to visualize at first. But now that we multiplied the first equation by 6, the second equation by that number, we end up with exactly the same equation, which means the two equations are the same. In other words, if we eliminate this equation or this variable from this equation, variable a, by subtracting, the b's are also going to be eliminated. So we're going to end up with just one equation. That means that is the equation, the only equation we will have. Because the numbers are not so easy to read, it wasn't very clear when we were going through this problem. That means that we have a free variable. You know, if this was a matrix, an augmented matrix, we would have, we would end up with something, after row reducing it, we would end up with 6 times negative 3 plus square root of 33. That is the column of the a's, 0, 24, column of the b's, 0, and then the third column would be 0 and 0. There we go. So we have a pivot here, and so that would be a free variable. By the way, we can simplify this, making this a, I don't really want to use a 1 here, because that means we would have to divide by all of this by, if I call B, I'm trying to think here. We can divide by 6. Um, Negative 3 plus square root of 33, divide by 6, and we end up with 4, 0, 0, 0, 0. So what that is telling us is that negative 3 plus square root of 33a plus 4b is equal to 0. Yeah, I guess there's no, and then another easy way to do this. So a is equal to 4 negative, because we're going to move this to the other side of the equation, over negative 3 plus the square root of 33b. And all we need is one eigenvector. Actually, there are many eigenvectors. This kind of shows that the eigenvector is not unique. There are many eigenvectors. So pick b to be 1, or choose b equal to 1. We don't really want to do 0 because we want a non-zero eigenvector. And so we end up with a equals this, and just b equal to 1. So we have the lambda 1 was negative 3 plus the square root of 33 over 2. And the corresponding x1 will be a vector, a column vector, where a is negative 4, or the first entry is negative 4, over negative 3 plus the square root of 33, and the second component is 1. So we have a lambda value with its corresponding eigenvector, or an eigenvalue with its corresponding eigenvector. So this is one part of the solution. Okay, let's go through the other one a little, hopefully a little faster. So let's see how we set it up. The other lambda, remember, lambda 2 is 3 plus the square root of 33 over 2. And we want to find x2. X2 equals question mark. So we have a lambda and a corresponding an eigenvalue and a corresponding eigenvector. Well, this is another eigenvalue we already know, but we do not know its corresponding eigenvector. So the way I figure this out is go back to the original matrix, 1, 2, 3, 4. I don't know what those are. I'm going to recycle A and B. I'm going to reuse A and B, but you can use any letters you want. And that should equal the eigenvalue 3 plus square root of 33 over 2 multiplied with the same eigenvector. So the trick is, the idea is a matrix times a vector gives us almost the same vector, except that it is multiplied with a constant. And this is the constant. Oh, by the way, backing up a little bit here. If somebody said, oh, can I make B any number I want? Sure. You can make it 2. And then you have to adjust this accordingly. And I'm thinking somebody who's very focused on keeping things simple could say, well, can I make B equal to negative 3 plus the square root of 3? Yep, those two would cancel, and consequently A would be negative 4. So what I'm trying to tell you is there are many solutions. This is unique, pretty much unique, but there are many ways to come up with eigenvectors. There's more than one eigenvector corresponding to an eigenvalue. However, please provide only one eigenvector. So I'm choosing my free variable to be 1, but you can pick any number and just stick with that one. So let's solve this system of equations. So we have A plus 2B. There is the A and the 2B, and that should equal 3 plus the square root of 33 over 2A. On the other hand, we should have that 3a plus 4b should equal 3 plus square root of 33 over 2b. And we want to find the eigenvector, so we want to find a and b. I'm going to suspect we're going to end up with the same kind of thing going on. So let's subtract from both sides. Remember, this is 1 minus this quantity. So we're going to have 1 minus 3 plus root 33 over 2a. Keep the 2b there, equal to 0. This equation has 3a in it, 3a plus 4. But then we're going to take away this fraction, 3 plus root 33 over 2b, also equal to 0. And I'm going to suspect we're going to end up with the same kind of thing, but let's go through the whole thing. So this is 2 over 2 minus 3 over 2, and that is going to give us negative 1 still. Oh, no, not plus, but minus, because we're subtracting, and that is going to affect, yeah. So we have minus square root of 33 over 2a plus 2b. And then here, 3a, that is equal to 0. Plus, that is 8 over 2 minus 3 over 2, that is 5 over 2. But then we still subtract the square root of 33. And then b, let's multiply by 2. So negative 2, negative 1, because multiplying by 2 only clears up the clears up the denominator, but the numerator stays as is, negative 1 minus square root of 33a plus 4b equal to 0, multiplied by 2, 6a plus quantity 5 minus root 33b is equal to 0. So the question is, are we going to end up with the same situation we had earlier? And I don't know the answer to that. The one thing I want to do is double check. 2 minus 3 is negative 1. 4 minus 3 is 5. Yeah. So instead of going directly to Cramer's rule, anticipating we may end up with 0 as the main determinant, what I'm going to do is multiply the first equation. I'm going to label this equation as equation 1 and the second equation as equation 2. And we're going to multiply the first equation by 6, multiply equation 1 by 6, and that's going to give us 6 times negative 1 minus square root of 33a plus 24b equal to 0. And we're going to multiply the second equation by negative 1 minus square root of 33. And multiply second equation by negative 1 minus the square root of 33. Okay, so we're going to end up with 6 times negative 1 minus the square root of 33a. And here's the deal. We got to multiply now those two. Well, this is the coefficient of b, and we're multiplying by that. Let me check something very quickly. and I see the mistake here. So I was going back to this papers. This should have been a 5. Yep. Um, in fact, this one should have been a 5. I'm not sure why I put a 3 there. I wonder how far back that is. The mistake is, whoa. I think the 3s are correct because the 3s came from 2 minus 5 and 8 minus 5. So those are correct. The 3s are correct. But then when I started out with a new, so that 3 appears to be correct. The lambda is the one that has the 5, but not necessarily the vector. And that kind of confused me here because then this should have been a 5. Remember, in the eigenvector here, rather in the eigenvalues, we had the 5 and the 5. Yep. And I think that's where I went wrong here. So that should be a 5, a 5. That should be a 5. That I believe stays as a -3. And then we need to, or I need to fix this. So this should be a 5, 5, 5. And then we have the same situation. 2 over 2 minus 5 over 2 is -3 over 2. Yeah. So this should be -3. And then 8 over 2 minus 3 over 2 is the 5. Rather, 8 minus 3 is the 5. Oh, but this should have been a 5 to start with. Okay. Yeah. So 8 minus 5 is a 3. There we go. Okay. So then when we multiply by 2, we still end up with 3 here. And this should be a 3. Okay. So this stays as a 3, changes into a 3. But then when we multiply, and here we're multiplying with a 3 instead of a -1. When we multiply this with this, we do end up with 33 minus 9, which is 24. And please take the time to multiply those two binomials on your own. So plus 24b equal to 0. And then we end up with the same equation. So that means that when we simplify, we're going to end up with zeros at the bottom. When we eliminate, rather. And that means really they are one with another. What I'm trying to say is A will be, if we move this to the other side of the equation, -24b over 6 times -3 minus the square root of 33. And then we can simplify the 24 and the 6. We can factor a negative out of those two, which will simplify with that. So we end up with 4b over 3 plus the square root of 33. There we go. So lambda 2 is 5 plus the square root of 33, again 5, over 2, and the corresponding x2, which is the vector, the eigenvector, will be, if we choose b to be 1, then a would have to be 4 over 3 plus the square root of 33 over, and then 1. Wow. This is a very, very long problem for our first problem of eigenvectors and eigenvalues. Yes. It is particularly long. They're meant to be long, but not this long in general. Let me just review this. So negative 5 plus root 3 over 2 is this eigenvalue with this corresponding eigenvector, negative 4. And if you want to simplify those two, go ahead. But don't forget that if you do that, then this turns into a negative 33. Yeah, so another way to rewrite this is to put 4 over 3 minus the square root of 33 and then 1. Those two are the same. So you can do that, and that will match this a little nicer. We have a 3 minus versus a 3 plus situation, and here we have a plus 5, and um, let me double check something here. Lambda 2 is 5. Let me go back to the lambdas. The lambdas are positive. So here, the lambda 1 should have been 5 minus the square root of 33 over 2. And the lambda 2 is 5 plus the square root of 33 over 2 with its corresponding eigenvector. Something to notice about the eigenvalues is that if you add them together, lambda 1 and lambda 2, lambda 1 plus lambda 2, in this particular example, that's going to be equal to the trace of the matrix A. Now, the trace of the matrix A, here it is, matrix A, is the sum of the diagonal elements, main elements here. So 1 plus 4 is 5. So lambda 1 plus lambda 2 should be equal to 5. And indeed, if we add the two lambdas we found, if we add those two, the 33s will cancel off because one is negative, the other one is positive. So we end up with 5 over 2 plus 5 over 2, which is indeed 5. Notice also that the determinant of the matrix is 4 minus 6, negative 2. Determinant of A is negative 2, and that is also equal to lambda 1 times lambda 2. If we multiply the two eigenvalues, okay, so multiply this out, and we're going to end up with 25 minus 33, because those are conjugates. You can actually do the multiplication yourself by foiling, but we will end up with 25 minus 33, which is going to give us negative 8. The 2's will multiply also, so we end up with negative 8 over 4, which is negative 2. And indeed, that is the case. When we multiply the two eigenvalues, or the 3, if there were 3, that is going to be equal to the determinant of A, and the two eigenvectors added together is going to be equal to the trace of A, and the trace is the sum of the diagonal elements. Let's do an example 2, and it will be a 3 by 3 matrix. And I was going to go with just a random matrix, but after the experience of, example 2, I was going to do a random matrix, but after the experience of what we just went through with example 1, I decided to search on the internet for a matrix with integer coefficients, with integer eigenvalues. So this one I found in a paper written by, I just tried to find one very quickly. So by Christopher Toes and Eric Campbell in a paper from 2016. So I just want to give proper credit to where I found this matrix. Yeah, so I wanted to just make one up, but I realized that it was taking me longer than what I wanted. So I just quickly searched on the internet, and I found a paper by those fellows. And here it is. So let's find the eigenvalues and corresponding eigenvectors for this matrix. Let's see. So, oh, to find the eigenvalues, we have to come up with the characteristic polynomial of this matrix. So the way we find this, let's label this as A. We gotta do A minus lambda I. So that is 1, 0, 4, 1, 3, 1, 2, 4, negative 1. And we're going to subtract the identity with lambda in the main diagonal. So it's not really the identity. It is the identity multiplied by lambda. And we will have 1 minus lambda, 0, 4, 1, 3 minus lambda, 1, 2, 4, negative 1 minus lambda. 104, 104. I'm double checking. 131, 2, 4, negative 1. All right. And now we want to find the determinant of this matrix. And we can do something fancy like subtract one from the other and so forth. Sometimes that takes longer than just plowing through, the cofactors formula. Sometimes I give the analogy that, trying to find an easier way is just sometimes longer than do nothing. So multiply those two and those two. So that is going to be 3 minus lambda times negative 1 minus lambda. But then we got to subtract that, the 4, this product. 0 is nice because then we can skip it. And then we include the 4 by cofactors. And we're going to multiply 4 minus 2 times 3 minus lambda. Okay, so this is our polynomial, but we have to, of course, expand it and simplify it, that polynomial. So that is equal to 1 minus lambda. Multiplying those out, well, 3 first terms, so negative 3, outer terms, minus 3 lambda, inner terms, plus lambda, last terms, plus lambda squared. But then we still have to subtract 4. And then we add 4 times 4 minus 6 plus lambda. All right, before I put this away, I just want to make sure 3 minus lambda is correct. Negative 1 minus lambda, and that comes from that. It looks like everything is correct. So 1 minus lambda, and then we have to simplify this guy. We have a lambda squared, and let's see, minus 2 lambda, and then minus 7. All right, and here we're gonna add 4 times negative 2 plus lambda, or lambda minus 2, and then we're gonna multiply this out. So we have lambda cubed minus 2 lambda squared. Actually, I'm multiplying with the negative lambda, so this should be negative lambda cubed plus 2 lambda squared plus 7 lambda. And then multiplying with a 1 gives us plus lambda squared minus 2 lambda minus 7 minus plus 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 minus minus, and then plus 8 minus, what am I doing plus 8? It's plus 4 lambda, and then minus 8. Let's change that plus 8 to minus 8. and then plus a 4 lambda. Okay, so we got negative lambda cubed. Let's look at the lambda squared. It's 2 lambda squared, and a lambda squared is 3 lambda squared. And then 7 lambda minus 2 lambda is 5 lambda, and 4 is 9 lambda. Yeah, plus 9 lambda. And then the numbers, negative 7 minus 8 is negative 15. So the characteristic polynomial is negative lambda cubed plus 3 lambda squared plus 9 lambda minus 15. And then we have to find the zeros of this polynomial. This is our polynomial with real coefficients and in fact integer coefficients. And so we can use the algebra, college algebra theorem that we usually see, which is the rational zeros theorem, which tells us that if there is a rational zero, it will have to be a divisor of 15. So the possible roots, possible rational roots, this should bring back memories from when you took college algebra. They are plus minus 1, plus minus 3, plus minus 5, and plus minus 15, because they are the divisors of 15 if the leading coefficient is 1. So we start checking them out. There's only 8 of them, 2, 4, 6, 8. And so it doesn't take too long to figure out what the solutions are. Oh, we're going to use synthetic division. Again, bringing you back. So negative 1, 3, 9, and negative 15. Some people would say, well, could say, why don't you multiply by negative 1? And that way your polynomial is going to be leading with a 1 instead of a negative 1. Yeah, we can do that if we wanted to. Sure. Let's try 1. 1 is one of our candidates. So bring back or bring down the negative 1 times 1 is negative 1. So we got 2 times 1 is 2. And that's going to be, 9 and 2 is 11. And that's not good, because 11 times 1 is 11, and we don't end up with a 1 as a root. Let's try negative 1 real quick. Negative 1, 3, 9, negative 15, negative 1, negative 1, negative 1. So we end up with 1. 3 and 1 is 4. So that is negative 4. When we add those together, we end up with 5. Man, that doesn't work, because we're supposed to end up with 0. Okay, so that makes me think maybe, because I was anticipating 1 or negative 1 to be a root, only because I had seen this kind of problem before, but otherwise I wouldn't know. However, going back to this, I think I made a mistake on the polynomial, which will cause this to be incorrect. Let's see. Let's just review some of the steps here. negative 6 plus 2 lambda when we multiply by 2. And I think I missed the 2 of the multiplication. Boy. So let's fix that. That would mean this is a 2 lambda. That causes problems. So we have 8 lambda, 8 lambda minus 8. Okay, and what does that do to this? Where did we add the lambdas? Here on the 9. So we had 7 minus 2 is 5 plus 8 is 15. And let me no. This should be 13 because 7 minus 2 is 5 plus 8, 13, boy. 13, so that is 13 lambda, negative lambda cubed, plus 3 lambda squared, plus 13 lambda, minus 15. We still have the same rational roots because those rational roots come from the last constant, the constant element in the polynomial, if we have a 1 or negative 1 on the leading coefficient. Okay, so that means this is wrong. Let's just cross it off and start dividing again. Negative 1, 3, 13, negative 15, 1. Let's try 1 this time. Again, with synthetic division. So negative 1 times 1 is negative 1. So that is going to give us 2 times 1 is 2. All right. This is going to work because now we have 0 as the remainder. So that means that 1 is a root, a solution to the, or a root of the characteristic polynomial. And we have a quotient of dividing by x minus 1. So what we have this far is that p of x, the characteristic polynomial, is x minus 1 times negative x squared plus 2x plus 15. Okay, we can factor out the negative because it drives me a little crazy to have a negative leading coefficient actually. X squared minus 2x minus 15, and that makes it easier also to factor. So we have x minus 5 and 3, so minus 5, and then x plus 3 will do. And now we have, oh, I switched from lambda to x inadvertently. All of those are supposed to be lambdas, not x's. Whoops. Lambdas, comma, not x's. And that means we have 3 eigenvalues. And I'm going to label this as number 1, number 2, and number 3. So the first eigenvalue is going to be 1. The second eigenvalue is going to be 5. And the third eigenvalue is going to be negative 3. That is arbitrary. If a student says, well, I want to label this as number 1, number 1, number 2, number 3, or any other order, that's fine. There is no reason to do one or the other. Okay, now that takes care of the eigenvalues. We still have to find the eigenvectors. Whoa. So we want to find a vector. This is a nice one. A vector ABC or XYZ, whichever way you want to call it, so that when we multiply the original matrix, 1, 0, 4, 1, 3, 1, 2, 4, negative 1, with that vector A, B, C. Now, since the eigenvalue is equal to 1, that means that we have to have 1 times A, B, C. And we want to find a solution. We want to bring this to the other side of the equation. So we want to take away an A. See, this is A, B, C, but we're going to take away an A from this side to this side. So we're going to subtract an A, and we're going to end up with 0 here. We're going to take away a B, and we're going to end up with 2, and take away a C, and we're going to end up with -2. I'm just double checking in my head, because again, we have A plus C equals A. Bring back the A to the other side, and then there's going to be no A. Okay, so this equation is equivalent to 0, 0, 4, because when we bring the A back to this side, the A from here is going to cancel off. Then 1, 2, 1, because when we bring this B to this side of the equation, the B's are going to cancel off. The 3 and the 1 from here is going to be reduced. The 1 is going to reduce the 3 down to 2. And then we're going to have 2, 4, -2. So we're really solving for this equation, A, B, C equals 0, 0, 0. Okay. And by the way, we're going to be able to verify everything we're doing after the fact. This is going to be way easier, I think, than what we did earlier. So the matrix right now is, is this one, and we can row reduce it. So we can do row 3 minus twice row 1, rather row 2. So we got 0, 0, 4, 2 minus 2, 0, keep the 1, 2, 1 here. 4 minus 4, 0, interesting. 4 minus 4, and then -2 minus 2, that is going to be -4. And then we can add this to that, or the other way around. We can add this to that. So we have row 3 plus row 1. So the last row is going to be zeros. 1, 2, 1. 0, 0, 4. We can divide the first row by 4. Row 1 divided by 4. And that's going to be 0, 0, 1, 1, 2, 1, 0, 0, 0. Let's move on to a new page, which means we can subtract row 2 minus row 1. And we're going to end up with 0, 0, 1, 1, 2, 0, 0, 0, 0. We typically put them, switch the row 2 and row 3, rather row 1. So we have 1, 2, 0, 0, 0, 1, 0, 0, 0. Okay, there's one pivot column. No, there are 2 pivots and 1 free column. The free column is this guy. By the way, this is equivalent to saying this matrix times A, B, C is equal to 0, 0, 0. A, B, C. Oh, that means that C has to be 0. Yeah, for this to work. Okay, so C has to be, because we have no A, no B, and C has to be this 0. So C has to be 0. And then B is a free variable. This equation says, or this row says that A plus 2B is equal to 0. A plus 2B plus no c is equal to that 0, which means a equals opposite of 2b. And that means b is a free variable, and we can pick b to be anything. In particular, we can choose it to be 1. We don't want to choose it to be 0 because we want to avoid 0 eigenvectors. Sometimes there's no other eigenvector than 0, but in this case, there are. So if b is 1, a is negative 2. So we end up with x1 equals negative 2, 1, 0. So what we claim is that this is the eigenvector corresponding to the eigenvalue 1. So that goes with lambda 1 equals 1. What does that mean? Let's make sure we understand what that means. That means that if we multiply 1, 0, 4, 1, 3, 1, 2, 4, negative 1 with negative 2, 1, 0, we're going to end up with negative 2, 1, 0. Well, let's see if that is true. I'm going to assume I don't know that yet. So negative 2, yep, that gives us negative 2. So the first entry is good. Negative 2 plus 3 is 1 plus 0, 1. So far, so good. Negative 4 plus 0, 0. Sure enough, if we multiply this vector with this matrix, we come back to the same vector. So that means that this lambda and that vector are eigenvalue and eigenvector of this matrix. 1 down, 2 to go. What is the second eigenvalue that we found? The second eigenvalue is 5. So lambda 2 equals 5. And we want to know the vectors A, B, C. So when multiplied with 1, 0, 4, 1, 3, 1, 2, 4, negative 1, that is equal to 5, because 5 is the eigenvalue, A, B, C. So we want to know all of those. Well, I'm going to go ahead and proceed the same way as we did earlier. We're going to take 5 A's away from 1 A, and that's going to give us negative 4 A's. Yeah, that's the 5. We're going to take 5 B's away from these 3 B's, and we're going to have negative 2 B's. And then 2A plus 4B minus C, but then we're going to take away 5 C's. So we're going to end up with negative 6, 2, 4. All right. And we want to end up with 0, 0, 0. We want to row reduce this guy. I'm going to do it horizontally this time. We're going to take the first row and add rather 4 times the second row. So negative 4 plus 4, 0. Negative 8, 8. Because we're adding 4 of those onto that. 4 of those, 4 of those. Leave this as is. 1, negative 2, 1. Now we're going to subtract from R3 twice R2. 2 minus 2, 0. 4 minus, whoa, that's going to be 4 minus negative 4. So that is 8. And negative 6 minus 2, negative 8. Okay, we can add this vector onto that, or this row onto that. So we're going to do R3 plus R1, 0, negative 8, 8, 1, negative 2, 1, 0, 0, 0. We can multiply the first row by negative 1 over 8, and that's going to give us 0, 1, negative 1, 1, negative 2, 1. Can you imagine doing this with those ugly fractions we started with in example 1? I cannot imagine. That would be a disaster. So this is a pivot. We want to get rid of this negative 2 by adding to the second row. We're going to add twice the first row. So 1, 0, because we're adding that, and then we're adding negative 2 to 1, so that is going to give us negative 1. Oh, and we have 1, negative 1, 0, 0, 0, 0. Now, our goal is not to put it necessarily on row echelon form. I just want to know the relationships between A, B, and C. So B minus C, B minus C is 0, and that means that B equals C. A minus C is 0, and that means A equals C. Interesting. So all three are equal, because if A is C and C is B, that means that B is A. Everybody's equal. So the eigenvalue, and we should check that, the eigenvalue 5 has a, and then we can pick, we can just choose a number. Let's pick 1. So if C is 1, so is A and B. So if we multiply the original matrix 1, 0, 4, 1, 3, 1, 2, 4, negative 1, with 1, 1, 1, we better end up with 5, 5, 5, which is 1, 1, 1 times 5. I can already see this is going to work really well, because the rows add up to 5. 1 and 4, 5. 1, 4, 5. 6, 5. So it works. So lambda 2 equals 5 has a corresponding eigenvector. So the eigenvalue 5 has a corresponding eigenvector 1, 1, 1. 2 down, 1 to go. So here's where I'm going to ask you to finish the problem. The last lambda, because there's 3 lambdas. I'm going back. Oh, the third lambda is negative 3. Lambda 3 equals negative 3. So what we want to do is find a vector, a column vector. We can start with A, B, C if you want to, so that we end up with negative 3A, negative 3B, negative 3C. That's what we mean by negative 3 times ABC. When we multiply with the original vector, which is the original matrix rather, which is 1, 0, 4, 1, 3, 1, and 2, 4, negative 1. Yep. So I'm going to let you finish this, practice finding the eigenvalues and corresponding eigenvectors for different matrices. And we're going to stop the video here.